Funnians, Albert here. How do black holes form? Well, you need a massive star first of all. But after that, how do you do it? That's the question we're going to be answering in this video. If you want to watch to the end, then please make sure to like and subscribe this video. It helps a lot, and you can also unsubscribe if you want afterwards, or dislike if you want afterwards. So without further ado, let's get to it. So, a black hole forms when a really massive star dies. So, for example, if you have a star over 8 times the mass of our sun, or 8 solar masses, which we denote using this symbol right here. If you have a star that has 8 solar masses or more, then that means that it is going to die in a supernova explosion. The way this happens is that the massive star caves in on itself because its core, which at this point is made of iron due to nuclear fusion, does not produce any more energy, because instead of liberating energy when it creates fusion, it actually needs energy to do fusion. Everything in the universe will eventually turn to iron, because iron is the stablest element. Both nuclear fusion and nuclear fission reactions end up at iron. So now that this massive star is caving in on itself, gravity takes over, and so the star's outer layers slam into the inner layers, which in turn makes them. Sometimes this can make them hot enough to fuse, and most of the time this makes them hot enough to fuse and repel the crushing force of gravity trying to push them into oblivion. But in this case, the star doesn't have any fuel to do this. Its core is made of iron. Iron does not liberate energy. So at this point, nuclear fusion cannot withstand the force of gravity. Inside the core, protons and neutrons, which you may have heard of before, slam together to create neutrons. They just create neutrons because the electrons. Imagine this is an electron right here. So basically, it spirals into the core, which quantum mechanics says that they shouldn't spiral into the core, but in this case, they have no choice. But another law of quantum mechanics, the Pauli exclusion principle, states that nothing can actually touch anything else because of the repulsive force between their electrons. But here that doesn't apply anymore. It doesn't apply because there are no electrons to speak of. It's just a sea of neutrons with a few specks of protons within. It's a neutron star. The iron core of a star turns into a ball of neutrons only a few kilometers across. Sometimes they can get up to 20 or 30 kilometers, but rarely ever bigger than that. Neutrons. Now the fate of a star depends on which side wins. If the neutron star wins, then it turns into a neutron star. If the if the gravity wins, it turns into a black hole. Basically, the fate is determined effectively by if the star is massive enough. Extremely massive stars will definitely definitely end their lives as a black hole. Less massive ones are a little more obscure. They have a higher chance of creating neutron stars, but still, most of the time they create black holes. But that's just one way to create black holes. And I'm not going to make a video that's just 5 minutes and 23 seconds long. So, let's continue. When we have a neutron star, neutron stars have a mass of around 1.4 solar masses. This is called the Chandrasekhar limit. Neutron stars have masses mostly around 1.4 solar masses because they come from really massive stars. Their iron core, and the iron cores had masses of 1.4 times the solar masses. Compressing them doesn't make it more massive. It doesn't add or remove material, so the overall mass remains the same. Of course, it does remove a lot of neutrinos, but the amount is so tiny because neutrinos are so minusculely small that they don't really apply. They barely even interact with gravity at all. So that means, that basically means that the black hole that a black hole probably doesn't form when theirs is 1.4 times the solar mass of the sun. Or does it? Sometimes it does. Of course, I did mention earlier that basically it's determined that basically if a black hole or a neutron star forms, it's determined slightly by random chance. But that's just, some observations over the past few years have determined that this is actually not the case. Neutron stars are incredibly dense objects, so there's a lot of material in them. They have 1.4 times the mass of a black. They have 1.4 solar masses after all. But that doesn't stop a black hole from having the same mass, right? No. Because black holes need to get masses of over 2.1 times a solar mass. So, which brings us to the second way of creating black holes: binary mergers. A neutron star can be a pulsar or a magnetar, whatever it wants to be. But really, it will eventually end its life as a black hole. Neutron stars do eventually die out. Everything dies out at some point. Over courses of hundreds of billions of years, they lose energy and die. Their masses the material inside a neutron star no longer has the angular momentum, the centrifugal force, the angular momentum pushing it out. Because if there was no angular momentum, then everything would just speed towards the center, and boom, you got a black hole. A black hole that shouldn't be possible. But when a neutron star stops spinning, then it no longer gives that centrifugal force. That centrifugal force is required. It's required for things inside the neutron star to stay apart. But when there is none, there's also no neutron star. The mass collapses in on itself into a black hole. Well, that's two ways. But let's get back to binary mergers. Binary star mergers are really, really cool. When a neutron star and another neutron star come together, they don't just stand still like this. No, they don't stand still. They rotate around. They rotate around their barycenter. The barycenter is basically the common center of mass. This black point right here is what I'm using for the barycenter. Basically, they orbit around that. I mean, that's not where the gravity is situated. The gravity is situated inside the neutron stars. But the center of mass, because, in general, in Newtonian mechanics, it's perfectly reasonable to say that the mass is outside the star. After all, it's just the idea of centers of mass. There's nothing wrong with it. Even Einstein's law of gravitation doesn't really affect this. It still stays like that. But neutron stars have a lot of mass. They have so much mass in them that they release that as energy. A lot of energy. Because E equals mc squared, they need to release that. They need to release mass, energy, into space. And that energy comes in the form of angular momentum around the barycenter. So the neutron stars will slowly start, over the course of around 2 billion years, the neutron stars will slowly come together. Boom! They collide. So but that's not the last way you can create a black hole using binary mergers. There are also accretion-born black holes. We currently haven't detected any, but there might be some out there. This occurs if a neutron star and a regular star, this diagram is definitely not scale. Neutron stars are definitely not a significant fraction of the size of a star. They are only around a few kilometers across, mostly. Eventually, yes. Yeah, massive stars can orbit neutron stars. It looks like they should have a bigger gravitational pull, but no, neutron stars are almost black holes. So you can't do anything about that. Basically, material closer to the neutron star can be more strongly affected by its gravitational pull than the star's own gravitational pull towards the center. So basically, material will start falling around the neutron, falling into the neutron star, making it gain more and more mass, and eventually that star, if it is massive enough, will give all of its mass away. The neutron star will exceed 2.1 times the mass of our sun and collapse into a black hole. But how efficiently this happens is frankly not certain, because if material lands on a neutron star, then that material is sometimes ejected away in massive X-ray explosions. Basically, when material comes onto the surface, it detonates because of the extremes of a neutron star and can be blasted away. So this process can take much longer than if normal neutron stars collide together. Just two neutron stars collide. This process can take much longer than 2 billion years. And so that's basically all the ways to form a black hole. Thanks for watching. Wait! There's actually one more way. There's actually one more way to create a black hole. Well, we haven't actually found that, so it isn't really a way per se, but it doesn't matter, okay? It's just one way that is possible. It is very possible because the laws of physics. Basically, imagine if there is a massive cloud of dust somewhere in the early universe, like this cloud or something, and sometimes if it collapses fast enough, it can create tiny black hole. It just skips nuclear fusion. Just creates a black hole instantly. So its gravitational collapse. There is basically no way to actually definitively confirm this without a time machine. The last time someone used one of those, things ended pretty badly. Looking at you, Nick Lucid from Science Asylum. Okay, well, anyways. Anyways, that is basically all the ways to create a black hole. For real this time. And as always, thanks for watching.